anybody want to go over that daily problem, or do we want to just talk about the gist of it?
Was it really just plugging into the equations we had?
Yep, pretty much.
Okay.
And then it was treating the second part. You were treating it just with the mass of the hydrogen. So what you found is the difference between the experimental frequency and the theoretical, just the fluorine staying the same, but the hydrogen's moving rather than both of them moving. How much of an impact does that have? And you can see that the measured values are not the same.
Yeah.
Yeah. Okay.
They're pretty far off, correct?
I didn't get them to be incredibly far off.
Like they're within the same magnitude, like
yes,
the 10th, but like technically we're off like quite a bit.
Yeah. Yep.
Okay.
So last time we finished up with a harmonic oscillator, and now we're going to go into another system. We're going to go to a particle on a ring, and we're going to find angular momentum that way. Before we do that, though, we have to talk about spherical polar coordinates. Okay, can we see that? No. All right. That's better. Okay, did you guys ever talk about these in physics?
Yeah.
It was Calc 3 that I talked about this.
Yeah, I also talk about Advanced Calc 2.
Okay. So rather than represent, could you tell me a little bit like what are spherical polar coordinates?
They're dictated by like two different numbers, just as Cartesian, but one's going to be a radius, while one's going to be like period, I guess, or whatever you consider the second one, depending on like how far away it is from the center.
Right. So instead, you're talking about how far away from that center point they are. So rather than talking about Cartesian coordinates, x, y's, and z's, we're talking about like a distance and then two angles. So rather than representing, geez, we're gonna try that again. Presenting, there we go. An object's location. With Cartesian coordinates, basically meaning x, y, and z. What we're going to do is we're going to use spherical polar coordinates. And we're going to have r, theta, and phi. So we're going to try to draw a three-dimensional system. We have our x, or excuse me, we'll do z. That way is x, and coming towards us is y. We'll try to draw that in blue. Actually, I'll hold off on that. Okay. We have some point R. So let's say we're talking about that point out in space. If this thing will ever focus, there we go. We have a distance R to that point. We also have two angles. We have an angle in the XY plane, and we have an angle in the XZ plane. So this angle we'll denote as theta. And we're going to mark where this point is in space. It's along that way. Then there's another angle here. And that's our phi. Does that plot make sense to people? Or can you see the three-dimensionality to it?
Yeah.
Okay. So the conversion, there's a conversion between the two. X is equal to r sine of theta cosine of phi. Y is r times sine theta again, sine phi. And then z is r cosine theta. And now our integration changes. So if one performs an integration, d tau, what was it traditionally? Like, let's say we were looking across 3 dimensions. What was it? So what did we do for like particle in a 3D box? What are our whatevers, our integrations? Integrands, is that what it's called? So what did we do for a particle in a 3D box? Or what did we do for a particle in a 1D box? D tau is equal to what?
It's just dx.
Yep, dx.
Okay.
So if we were looking across 3 dimensions, what would this be?
Dx, dy, and dz.
Yep. Now, if we translate that to spherical polar coordinates, it changes a little bit. We have a factor of r squared sine theta. And then what else do we need in here? So we had 3 variables, dx, dy, dz with Cartesian. What's it going to be for spherical polar coordinates?
dr, d theta, d tau, or not d theta.
Yep.
Circle slashes.
Yep, there you go. Okay. And with a lot of trig, we can show the following. I don't really want to show how to derive it, but we need to use it.
Oh,
So unless someone really, really wants to. A lot of trigonometry one can show. And do you remember what that what this meant?
Isn't that curl?
Yep, it's curl. So what is curl?
I don't know. I just learned the word.
Well,
it's not the same as flux.
not the same as flux, that's true. Curl, or this is a delta. So when we were looking at deltas for kinetic energy, what was it? Or how do you know that we're talking about something that relates to kinetic energy? What common mathematical term you see?
math, mv squared.
Yep, that's true.
Velocity.
Yep, you see velocity. What about in our class? What have we seen a lot whenever we're talking about the kinetic energy operator?
Is it the second derivative? Kind of?
Yep. We're
Okay,
talking
that's what
about
you're
second
looking for.
derivatives. So this means a second derivative in 3 directions. Okay. But that's not spherical polar coordinates. How does this translate to spherical polar coordinates? It turns into this junk. We might get another cat visitor today. I don't know.
Oh,
I think I'm going to run out of space. Shoot. Sine.
Wouldn't those R squared? Can't, or are you just trying to show it all right now?
Nope, they don't. They don't actually cancel because the order
Oh, because they're
matters.
operators technically. Gotcha.
And we got one other thing down here. I had to write it on another line. I'm sorry. Whew. Okay. So it's important to know which ones are thetas, which ones are p's. So this doesn't look like it's any simpler. And to be quite honest, it's not. But in some cases, we'll have to use it.
Great.
Let's say we were talking about a 2D system. Only 2D. How is this ugly thing going to change?
shouldn't there be an r squared sine r in there?
R squared sine R.
Like for the other two, there's an r squared sine theta.
Mhm.
Why didn't the first one have like a sine in it?
Oh, this one?
Yeah.
Just mathematically, it works out to not be that way.
Oh. Shut up. Tom.
It's great reasoning.
Yeah,
Yeah.
it just boils down to when
It
you
is.
do all the trig, it just doesn't happen.
Okay.
Just don't be like that.
Sometimes we have to be like that.
I feel like that sometimes.
Get in here. Okay, so everybody got that scrambled down. Now let's say we were considering only 2 directions. We're going to look at, hey, cat's scratching the wall. Fine, you're getting out. Get out of here.
He's yelling at the cat.
Better than a kid. That'll be next year while you're quarantined, right?
Get out of here. Yeah.
Yeah, just kick it in the butt, you know. My daughter will be okay with that, right? So we're talking about 2 directions. This boils down to just this. We can show that. Right now, we're not going to prove that, though. We're just going to use it later. Okay. So why did we have to talk about this? Well, we're going to use this in a moment when we talk about a particle and a ring. Am I all right to move this?
Yeah.
Go for it.
1 second.
Oh, all right.
You're good.
Okay, so we're gonna do another model system, and we're gonna get something out of this. We're actually gonna find a new quantum number from here. Okay, so let's talk about 2D rotation. Oh, you can't see it. 2D rotations, and this is particle on a ring. Your book, I think, just says 2D rotations. It doesn't say particle on it. What we're going to do, we're going to consider a quantum particle of mass m moving in a circle. And having a fixed radius. So the particle is going to travel around in a circle and it's going to stay within that circular pattern. It's not going to move in and out like close to the center, or excuse me, close to the origin and further away from the origin. It's going to have to stay on that line. Okay, and a fixed radius r. The potential energy is fixed. Is fixed. And we can arbitrarily set it to 0. That's what we're going to do. So of course, like this pen I can move up and I'm increasing its this potential energy. But if we say the 0 of potential energy is here, then if we're measuring differences, that's all that really matters is from the difference of that arbitrary point we set. Very similar to a lot of the like state functions that we talked about in physical chemistry 1, right? Okay, so let's try and draw this system out. We're going to have a particle. So we have our x and y axis. We're going to draw them looking flat down. So we'll do y, x. We have a mass out here. So here's our quantum particle. It's traveling in a circle, even though mine looks like an oval. This distance is r, and we have to have one angle. We're going to define our angle along here. And we're going to say that's phi. Okay, so everybody feel like they got an idea of what this system looks like. Just particles zipping around in a circle. Okay, so we're going to start with some questions. First question. What does the Schrodinger equation look like? Same question we ask for all of our quantum systems. So what's the generic form of the Schrodinger equation again?
H trident and trident, and there's a hat in there.
Yep, there's a hat in there. Yep. Hamiltonian operator operates on that wave function, get the energy out in that wave function. Okay, let's delve a little deeper. What's this Hamiltonian going to look like? We always have that fact. So we got the kinetic energy part and the potential energy part, right? E side. So let's look at the kinetic and the potential energy. Kinetic energy operator, what's that going to look like?
H bar squared.
Mm-hmm.
It's a negative over 2m.
Yep. And then what else do we need here?
The d squared over dx squared.
Yep. And we have an x direction. What else do we need?
And then dy.
Yep. Okay. So that's the kinetic energy portion. What about the potential energy?
It's going to be angular momentum.
It will be related to angular momentum, but
Just having it 0 for now.
yep. Yep, we set it to 0 for now, just to make our lives easier. So,
Never mind.
It's kind of
Zero.
cheating.
but Maddie, we totally could do that. It's
No, I'm just
gonna make
joking.
our
I don't
problem
cry.
better.
I don't cry over people.
Okay,
Just in
you're crying. I'm sorry.
No, I'm not.
Sorry.
She says she doesn't cry.
Sorry.
I feel like there's been a lot of tears lately. It's pretty normal, right?
I mean, we all get A's.
Yeah, nowadays.
That'd be so silly. Almost.
All right. The problem with this is, though, we can't actually separate our x and our y from one another with the setup we have. So, however, we cannot separate x and y variables. From one another. So we have two options. We can either give up, or what's our other option?
Change majors.
Rearrange things.
Giving
What's
up
that?
sounds pretty good.
Change majors.
Change majors? No.
Withdraw.
Withdraw? No.
Yeah, pass fail? No.
Yes, pass fail.
Oh
Yeah,
yeah,
we
is
might
that
do
even like an
pass fail,
option
yeah.
that they're considering?
Yeah, they might be. I don't know.
Yeah.
We're gonna all talk about it tomorrow after your inorganic class. If there's a big meeting about it. But in this case, we're not gonna give up. What are we gonna do?
Rearrange.
Rearrange? That's a good idea. We could always do that.
Multiply by something.
They multiply by some. Josh, you sounded so upset about that. Like, enough of this. All right, we're gonna go
Set
to.
something to 0 again.
No, we're not gonna set anything else to 0. We're gonna go to spherical polar coordinates. So that way, we're gonna transfer from these Cartesian to spherical polar. And what's gonna happen is we're gonna distill down to just hopefully one variable. That's the goal. Make our lives easier. So let's try spherical polar coordinates. And what are the only two spherical coordinates that we have in this system?
X and Y.
We have x and y. Those are the Cartesian ones.
That'd just be R and theta.
Yep. Is this one theta or phi?
I thought that's phi. Theta has the little squiggly in the middle.
Yeah, theta is this guy, right?
Yeah.
Yeah.
I get them mixed up sometimes. Okay.
I
And
never
now
draw the
Maddie's.
line the right way with the other one too.
Yeah. Maddie said something about angular momentum, and we got to talk about angular momentum. So whenever you see something traveling in a circle, we can talk about it. So to do this, we need to consider angular momentum. And it's given the symbol capital L in most cases. Does anyone remember what L or angular momentum is from their physics class?
It is MVR.
Yep.
Okay.
Wow. Okay, John.
Dr. John.
We should start calling him Morgan because he knows all the answers.
Hey, Morgan was a graduate student. He should know a lot of the answers. So, was it interesting to have another person around too, or was it like?
It was weirder yesterday that he popped in like halfway through.
Yeah.
I accidentally clicked on his thing once, and I didn't know how to get out of him being my first
And he
screen.
was like, huge on the
So
screen.
it's just Morgan on the screen.
5 minutes.
Oof.
So, John, you're right. It's MVR. What I have an X here. This isn't a variable. What is this?
The direction.
No, not a direction. Have you guys ever talked about
Cross
cross
product?
product? Yeah, there you go.
Oh. Forgot about that little guy.
Yeah, it's different than the scalar product, which we use a lot. What's M?
Mass.
Mass.
Yep. V,
Velocity.
Velocity. Is that V like vector V? Should be because it.
this is velocity. It is a vector.
Yeah. Okay. So isn't I forget how to like represent. Isn't that like V? Not V hat.
You could do V arrow
Yeah. Okay.
like that. Same with R. Yeah,
Yeah.
R is also a vector. And this R, that's just our radius, right?
Uh-huh.
We could also express this in terms of momentum. So let's say we wanted this in momentum. Do you remember what momentum is?
Mass
Mm-hmm.
times
Yeah.
displacement.
Not displacement, but
Mass
velocity.
times accelerator. Yeah.
Force.
So we could do P for momentum and R. Okay. So now, since we're in a three-dimensional system, we could have we could break this into different components. Like Josh said, these are vectors, right? So we could break this down into individual components in the X, the Y, and the Z direction. So am I okay to move this out of the way?
Mm-hmm.
So splitting L into its components. Oops, hit the camera. L sub X, L sub Y, L sub Z. Lx, since it's a cross product, it's Y times momentum in Y minus Z times momentum. Well, should be Y, I think. Then we have L sub Y, it's Z times Px minus X times momentum in Z. Lz is X times Py minus Y times Px. So we have three of these options. If we know one of them, we know the others. So we're going to ask the question, which do we want to use?
Is it a capital P or a lowercase?
It's meant to be a lowercase p. So of these three components, which of them do we want to use and why?
Probably
Why is
the
the top-
Lx.
Oh, what was
Why
that,
is
Quan?
Lx
Momentum
PY
of the Y.
What was that, Maddie?
Why is the LX PY? Shouldn't it be PZ?
Lx. It should be PZ up here. I'm sorry.
All right, well, backwards.
Yeah.
Idea.
There we go.
Now you could say it's easy peasy.
Yeah. Easy peasy lemon squeezy.
Oh, we got jokes today.
Yes.
Oh yeah. And that's dad level right there. I gotta start practicing. What were you saying, John, earlier?
Oh no, my idea kind of went out the window with it switching to PZ.
Okay. So which one do we want to pick?
Can't you use Ly and Lz? Or
You could
L-
use,
Lx?
yep, you can use any of them.
Oh,
But which one specifically do we want to use? And why?
because we have Py and Px.
Yep, exactly. We want LZ.
Okay, doctor.
You know it.
It has only X and Y in it. And that's how we use to describe our system so far. Okay, so now we know what LZ is equal to, but since we're dealing with a quantum system, we have to know about operators. So let's look at the LZ operator. What would the LZ operator be? So we have this expression for LZ. If we do LZ hat, everything else in here becomes an operator. So we're going to get X hat feel like I moved something around. I'll check it later. It's actually X hat PX hat minus Y hat EY. So it looks a little bit different than what we had previously written. All right, let's plug in for some of these operators though. We're going to leave X there. What's PX hat though? You remember?
The negative I8
Yep, negative I H bar.
DDF.
EX minus Y hat.
Negative I H bar DDY.
Yep. Okay, so how can we simplify this? What can we pull out?
Negative
Yeah,
8.
negative IH.
Yeah, negative I H bar. Then we get X hat E dx minus Y hat dy. Okay. Okay, so now let's return to our Hamiltonian operator. We already defined our Hamiltonian operator. What was it again? Negative H bar squared over 2m. What else do we have there?
D squared over dx squared plus d squared over dy squared.
Yep. Okay. But we don't want, how do we want this to look? We don't want x and y. What do we want?
Down to a single variable.
Yeah. We want this in terms of r and phi. So let's try and do that. Okay, recall, we had that big long expression that we were talking about. When we were discussing polar coordinates a bit earlier, that this was also equal to this expression. Like that. Does that look like it's improved our lives in any way, shape, or form?
No.
No.
It looks like we've just taken two terms and we've split it into three terms. That doesn't look too helpful. But there is something with our setup that is going to make this helpful. What do we know about any of these variables?
R is 0.
R isn't 0, but R is constant, right? So
Mhm.
R is a constant. R is fixed
So the variable is always gonna be 0.
and is a constant. So therefore, how does our expression change? So it started off as this. So how is this going to change if R is constant? What happens to this term?
Goes away.
Goes away. That one's 0. What about this one? Oh, except I forgot it. Is that right? Can I get a squared or just 1?
It's just D over D. I think it's what you wrote on the last one is just
Yeah.
R.
There shouldn't be a squared there.
dr.
Oh, okay.
Yep, so this term 0, what happens to this term?
Drops out.
So it'll be 0.
0, and then
Well, I
we're
guess
just
kind of
left over
happens.
with that guy, right? Okay. So therefore, our Hamiltonian's going to change. Therefore, h is equal to that negative h bar squared over 2m. We had this previously. But that's going to change a little bit. We get negative h bar squared over 2m. What happens on the inside of this bracket?
Changes to 1 over r squared, d squared, d psi.
Yep. So, oh, we should have a squared there. What can we do with this? We can just pull that r squared out and we're left over with oh, that should be a squared. So we get this as our expression. How does that benefit us from what we originally had?
0 is only one of the variables.
Yeah, now we only have to worry about one variable instead of two. So now we only have one variable. Which is awesome. So let's see what happens to LZ, that operator. So what about LZ hat? So originally we had LZ hat was equal to negative I H bar, oops, X hat, X plus Y hat, UY. If we change this to polar coordinates, this becomes LZ hat is equal to negative I H bar U phi. So that becomes simplified too. Okay. So now we want to get an energy expression like we have in the past. So let's go back to the Schrodinger equation and let's see what we can get. So let's return to Schrodinger equation. Because we can get two things from considering this. We can get the energy. What's the other thing we're probably going to get out from this? What have we always done? We found an expression for the energy, and we looked at something else with this.
Like, so why can we say that? Why can we say that d dx plus dy dx is equivalent to d d psi?
So how does that work out?
Yeah, how does that work out? 'Cause-
Mathematically, it does work out to be that way.
Okay.
So
Because I
it
mean, I
isn't-
was just gonna say that isn't exactly what we proved before. We did like the squared.
Right. We didn't prove this. There is a
Okay.
proof in your book for it. It's not overly complicated, but it's going to eat up time to get us this result. Like the important point is that we have two. How do we make two variables into one variable? So we showed that once. So I mean, if you want, we could show it again, but do you feel comfortable?
I was just wondering.
Yep, just falls out of the mathematics.
All right.
So when we go back to the Schrodinger equation, there's a couple things we can get out. First thing is we always get an energy term. What's the other thing we've done with our previous model system that we've also figured out?
Momentum.
What's that?
Momentum.
Momentum. Yeah, we usually find momentum somewhere like that, but there's one big one. We always find the energy. Then what do we usually do after that energy? Or what else are we missing? We know this. We know this. What else do we want to know?
What is the wave function?
Yeah, we want to know what the wave function is so we can predict its behavior. So we're going to try and find this. So we know these things. Well, we don't know these two. We don't know energy yet. Let's try and find expressions for these things. So what else we do know is negative h bar squared to r squared. We've just plugged in for that Hamiltonian. Has to be equal to that guy. Right? Okay. We're going to simplify this a little bit, the simple bottom part. Does this look familiar to anybody who's taken physics?
Oh, looks like something I just don't know.
It's been a while, probably, for most of you.
Yep.
This right here, mr squared, is actually equal to I, which is the moment of inertia. Oops. So we can make this look a little bit simpler if we want to. Your book does this, it expresses it as what we're going to write more frequently than this form. So negative h bar 2I equal to this. So you're more likely to see this in your book than this top expression. I prefer the top one a little bit more, but you'll just see that. Okay. So now we're going to ask another question. It might not seem like it's going to lead us anywhere, but I promise you it will. What is LZ hat squared? So we said LZ was equal to negative I h bar E phi, right? So what's LZ hat squared going to be?
Just h squared.
So it's all of this stuff
And
squared,
second
right?
derivative.
So
Got negative 1 squared, I squared, h bar squared. And what happens to this? We square it.
Yeah, it's gonna be -1. I guess the same, but h squared.
wouldn't I just go to 1 then? Because it's multiple.
Yeah, I goes to -1, so this is -1. What happens to that guy?
Just was +1.
Go to 1.
Sorry. You telling me to shut up? That becomes a +1, h bar, and then that second derivative. So everything together becomes negative h squared. That guy, right?
I still don't really get how you get, like, just because you square something, it becomes a second derivative.
It does if it's all scalar. So like LZ hat times LZ hat is equal to all that stuff. So we have h squared times
Gotcha.
that. And if this is a real quantity, then you can put them together. But the order matters. What we're saying is it's LZ squared. Like that's the operator is this. kind of like that. It's just the notation is a bit simpler that way. So if there's nothing for that function to operate on, it just works out to be that way. Okay, so I'm going to leave you guys in suspense with this equation. Ooh, and we're gonna look at that. We're gonna find an energy expression, and from that we're going to determine our wave functions. Are there any questions about the material at the moment?
Is our daily problem going to be based on this stuff?
Let me look. I don't remember. Let's see. It is, but it has to deal with using the energy expression that we're going to derive, but you'll want to look in your book what that energy expression is. Okay?
All right.
All right. Any other questions? Okay.